Good morning, everyone. So we're going to pick back up on Lewis structures here. We're going to start back with nitrate. We were kind of ending with nitrate last time, so let's come back to this Lewis structure for NO3 minus. And so when we're doing Lewis structures, one of the things we want to make sure to do is add up the valence count for each of the atoms, so we show the proper number of electrons. So 5 for nitrogen, just based on the row nitrogen's in on the periodic table, 3 times 6 for oxygen, and then plus 1 for the negative charge. And so that gives us a total of 24 valence electrons. This is a very important step to make sure we get the right number of valence electrons. And then we single bond atom. Let me actually draw this way here. So we have 3 oxygen atoms. We'll complete the octet to the oxygen atoms with a lone pair of electrons. And then for nitrogen, we have to think, are there any leftover electrons that aren't assigned yet? Well, that's all 24 electrons we have available, so there's none left over to go in the central atom. So I don't put a lone pair on nitrogen. But now I notice that the that the central nitrogen atom has a 2+ formal charge. It only has 3 electrons closest to it, and it should have 5 for a neutral charge. So that's how I calculate a charge of +2, is it should have 5, nitrogen should be surrounded by 5 electrons, it's only surrounded by 3. So that's a net charge of +2. So nitrogen has a net charge. Each of the oxygen atoms' formal charges are -1. So the charges on oxygen are 1, 2, 3, 4, 5, 6, 7 electrons surrounding each of those O atoms that only should have 6 for a neutral charge. So if an O atom has 6 electrons in its valence shell, it has a neutral charge. We have 7 here, that's -1. So the formal charge on all the O atoms in this Lewis structure so far are -1. And so now the question becomes, do I have room for electrons on that central atom of nitrogen? And I do. I have an open valence, so I don't yet have an octet around the central nitrogen atom. And I also have a positive charge to pull those electrons in. So let's pull in a pair of electrons to make a double bond. And then in doing so, we're going to change the formal charge of nitrogen now to be 5 - 4, because I have now 4 electrons closest to nitrogen, knocking the formal charge down to +1. And so that's good. I've reduced the magnitudes of formal charge. If you recall, the rule for considering multiple bonds to satisfy the octet of the central atom is that we should do so if the result is minimizing magnitudes of formal charge. So I've gone from -1 and +2 now down to 0 and -1 formal, down to 0 and +1 formal charges on the O and the N. And so then that's a better Lewis structure. Now you might think, can we do this again? Because I still have a positive formal charge on nitrogen, so why not do this one more time, make another double bond? So if we want to do that, let me sketch this up here. We might have this Lewis structure here, which you might think looks like a good idea because it now makes the formal charge 0 for this oxygen, 0 for this oxygen, and now nitrogen's 0. It now has 5 electrons closest to it, so it has 1, 2, 3, 4, 5 electrons closest to it, so 5 - 5 for neutral. But the problem for nitrogen is it's now expanding its octet past 8 electrons. So when I count the octet, I count all the electrons kind of in total, counting all the bonding pair electrons. That shows me 10 electrons for nitrogen, and that's just not possible. So the max is 8 electrons. So we have to stop at a Lewis structure that looks like the first one that we drew, which is 1 double bond between N and O, and then 2 single bonds between the other oxygen atoms. And so we can't go to this Lewis structure here. And so now for third row atoms, we'll see it might be possible for us to consider some Lewis structures. So the key is for a second row atom, we cannot expand an octet for any of the atoms. So if you have an oxygen atom, a nitrogen atom, fluorine, you cannot show a Lewis structure that's valid that will have more than 10 electrons, more than 8 electrons around those atoms. Okay, so then when we get back to nitrate though, what if we had said, well, why don't we draw the double bond here and keep this one single instead? So does it matter which of the positions I make the double bond with? And so I might notice that I can come up with 3 different structures where I'm just like moving the double bond around. One of the ways I might think of doing this is if I make this double bond here, and then I go back to putting those electrons back on oxygen, I arrive at this Lewis structure here. Or I could consider, well, why don't I make the double bond over here and then return the electrons back to that O here, so that would lead to this structure here. So I'm just kind of noticing that it turns out I can sketch three equivalent Lewis structures that are yet different from each other in which atom's making that double bond. So when we realize, or we start to notice for this structure, there's actually three different ways I can sketch the Lewis structure. It actually turns out the molecule does something kind of interesting. The real molecule actually turns out to never exist as what we might call A, B, or C. So the molecule is really never A, never B, never C. What it's going to do, it's going to find a way to exist as the average or the composite of those three structures. And so the average of these three structures would look something like this, where we have kind of a partial bond spread across those three oxygen atoms at all times. And so what this looks like here is the case where all three of these bonds are kind of not quite single bonds, not quite double bonds. If you kind of count the number of bonds, we have 1, 2, 3, 4 total bonds. So we have like 4 bonding pairs of electrons and any one of those three Lewis structures that are being spread across the 3 actual NO bonds. And so the 4 is the number of bonding pair electrons. So I have 4 pairs of bonding electrons. So again, that's just counting 1, 2, 3, 4 bonding pairs of electrons, and then being spread across the 1, 2, 3 connections to O atoms, being spread across the 3 NO bonds. And so now let's think about just generally what a single bond has 1 pair across 1 bond. A double bond has 2 bonding pairs of electrons across 1 bond, and then a triple bond has 3 bonding pairs across 1 bond. So if you think of what we're calculating here, something called like a bond order. And so if we're calculating this as our bond order, it's just somewhere between single being less than 4/3, being less than double. So a single bond is 1, bond order of 1. A double bond is bond order of 2. So a single bond, 1 pair of electrons across 1 bond. A double bond, if we have a double bond, that's 2 pairs of electrons across the 1 bond. So think of how the 4/3 is telling you have like a 1 1/3 bond across the N and the O. But that's at all times. So like if we're looking at a real nitrate ion, if we had the ability to see it up close and personal, we would actually see all 3 bonds are equal in length. We wouldn't see one shorter, double bonds are generally shorter. We wouldn't see one shorter bond and 2 longer. We see nitrate actually looks like the real composite. The next slide shows us how this is possible. So let's move to the next slide real quick and take a look at this. And so this is kind of one of our Lewis structures of nitrate where we have the double bond between one of the N and the O's, but the real molecule, what it does is it finds a way to align orbitals simultaneously so that you get the overlap of a set of p orbitals. This is a slide from chapter 9, so we'll try to understand this a little more next chapter where this is coming from. But what the real nitrate ion is able to do, it's able to take orbitals on all 4 of those atoms and simultaneously overlap them into one orbital such that that double bond is spreading across all those atoms simultaneously. And so what we call this picture here, we call this delocalization. And delocalization is good. That's how charge is being spread across multiple atoms. That adds stability to nitrate. This is one of the reasons why nitrate is such a stable ion. And then the real molecule never looks like the localized bond. So the real molecule never really looks like one of the Lewis structures that we sketched. So if you go back to the Lewis structure that, say, looks like this, that nitrate really never looks like this Lewis structure here. So it serves as kind of a idea to go back to kind of what a Lewis structure is meant to do. It's a model. It's trying to help us understand what types of bonds are involved between the atoms, where are lone pairs, are there lone pairs in the central atom, how many lone pairs are on the non-central atoms, and then how do we best understand maybe some of the geometrical properties of the molecule. One of the important geometrical properties of nitrate is all 3 bonds are equal in length. So all 3 bonds being equal in length is like an experimental measurable property of nitrate. And then it's something we can get through what we call resonance. So we call the effect of the electrons moving through a structure like this simultaneously, we call that like resonating. So the idea is that the electron pairs resonate at all times across the molecule, and it's never a back and forth. It's not like it's going from, like if you go back to the last slide where I had A, B, C shown, it's never going from A to B to C and going back and forth. It's just the electron pairs at all times spread across those 3 bonds through what we call and think of as what we term resonance. So we have a few more examples that we can show. There's a lot of molecules that have resonance. Another molecule that shows this is ozone. So if you think of ozone, which is an allotrope of oxygen, so we have O3, so we have a central oxygen, 2 oxygens connected. And so if I follow my usual Lewis structure rules, and I start with, 3 atoms, one of them has to be the central and the other 2 are the outer. So there's really, with 3 atoms, you have to kind of linearly connect them. So coming up with one of the O's is in the center, 2 oxygens connected. We have 3 times 6 for 18 electrons available. So I have 8 electrons here, 8 electrons around the second O, the second outer O. So that's only 16 electrons used. I have 2 left over to put onto the central atom. And so that central atom, kind of like nitrate, has a positive charge. So the formal charge on that central O should have 6, only has 4. That's a +2 formal charge. Only has 6 electrons surrounding it. So what we can do for ozone is we can pull in a double bond, lose the electrons here, make a double bond. That kicks that formal charge down to +1. So our formal charge is now plus on that central O. And then our outer O that we still have a single bond has a formal charge of -1. Should have 6, but it has 7. And then this O here is neutral in charge. But then ozone, just like nitrate, can have and show the effect of resonance. And so the effect of resonance would be we can kick this electron pair into here and then move this electron pair back onto that O here. And so now we have an O- on the left side, and then still a central positive charge, and then a 0 over here. So the initial structure we start with -1 and plus on the center. And so we're just resonating that electron pair, but at all times. So again, it's not a back and forth. It's not an A to B going back and forth. It's just at an all times, the electron pair distribute across both those atoms equally. So if you look at ozone, the charges on the outer O's, they look identical to each other. The charges on the outer oxygens are both the same as each other. In ozone, we have a positive charge building up in the middle. We have about -1/2 charges. How would we predict or calculate we have roughly -1/2 formal charges and negative charge building up in the outer O's? Well, it's because we're just, it's like the average effect of the 0 and the -1 charge. And so if you just go between 0 and -1, that averages out to -1/2 on either O, and that's at all times. So at any moment, the charge in each O is about -1/2, the central O always being +1 in both of our Lewis structures. So again, it's not a back and forth, it's at an all times. Ozone looks like it does in this picture here. And then the bond distance, if you calculate the bond distance here, that is equal to this bond distance here. So a lot of times we might, in terms of a Lewis structure, kind of just show this here. It's hard to then balance the lone pairs. So if I'm going to show a Lewis structure like this, I'm usually kind of showing the lone pairs maybe with their resonance structures here. And then I'm just showing that these bonds here are not quite single, not quite double. And it's not that one of them's double, the other one's single. These are averaging out to spread 3 bonds. So we have, I think it's pretty obvious, but just to make sure we're showing, you have 3 bonds. So the double and the single in any one of those Lewis structures. So that's our 3 bonds. And then we're going to spread those across the 2 connections to O. So we have 2 bonds here, the 2 OO bonds. And so those bonds are kind of, if you start to think of like what bond length they are, what bond distance they are, the bond length will be shorter than like a single bond, but then a little bit longer than a double bond. So double bonds are usually shorter. This is going to come up in a minute. We've talked about this a little bit, but double bonds are shorter, single bonds are longer. The ozone bond would be like right in the middle of what we'd expect for a double bond and a single bond. So bond order is about 1.5 for ozone. Now, calculating bond orders, I wouldn't worry about that for the test. It's just, for me, it's helpful to kind of try to understand through the Lewis structure that you can kind of predict like a bond length trend just based on sort of what you expect for that bond to be not quite double, but not quite single, but both the bonds to be equal in length. So both the ozone bonds are equal in distance in the ozone molecule. So a lot of other molecules will show the effect of resonance. Another one is a nitrite. ion, NO minus, so 5 plus 2 times 6 plus 1 for the charge. That's going to add up to 18 electrons. This will have a Lewis structure that looks very similar to ozone. So we'll start like we did with ozone. And then that's 16 electrons, the 2 electrons left over, onto the central nitrogen. Nitrogen's formal charge should have 5, it only has 4, so we have a positive formal charge. So we make a double bond, and then we can also, in the process, reduce the formal charges down to 0 and 0 for those atoms. And then sometimes we show with the resonance arrow, we can then resonate those electrons over to here. So now my Lewis structure rule is, like anytime I can sketch, like I did here, equivalent Lewis structures that are different from each other, the real molecule, the real structure just goes to the composites. We have to think, well, what's the average of these structures? Just very simple, we just look just like kind of ozone did. Like we have 3 halves bonds instead of not double, not single, somewhere in the middle. And so roughly 3 halves bonds for nitrite ion, just like ozone. Now, what about sulfate? Sulfate's kind of interesting in a few ways. So if we look at sulfate, calculate its valence electrons, 6 for sulfur, it's in the row of oxygen, 4 times 6 for the 4 O's, plus 2 for the minus charge. That's 24 plus 8, that's 32 valence electrons. And so in this Lewis structure, we'll have a central sulfur, throw our 4 oxygens on. Again, I'm not always showing three-dimensional the three-dimensional shape of the molecule. So the molecule may not be flat. Just try to have in the back of your mind, we're not always trying to show you the shape of the molecule with the Lewis structure. We'll talk about shapes that molecules adopt in chapter 9. And so I just follow my Lewis structure rule, lone pairs on all the non-central atoms. So that's 8 around each of the O's. That's 32 electrons. None left over for sulfur. Now, sulfur in some ways looks pretty good because it's satisfying the octet rule, so that's generally a good thing. So we have 8 electrons around sulfur, but we do have a positive formal charge. Sulfur should have 6 electrons surrounding it. It only has 4. That's a plus 2 formal charge, and the oxygens are all minus because they're all should have 6. They have 7. And just as a quick double check, if you sum up all the formal charges, so minus 1 times 4 plus 2, that equals minus 2. So you should be able to get the overall charge of the molecular ion. If it's uncharged, all the formal charges should add to 0. This is a minus 2 ion, so all the formal charges should sum up to minus 2. So minus 1 times 4 plus 2 equals minus 2. So you can always do a quick double check on formal charges. But now, so the question would be, is this the best Lewis structure for sulfate? And in a lot of ways, it probably is the best Lewis structure for sulfate, and we should just say, don't even consider doing anything that might expand the octet of any atom because it seems kind of crazy to do so. But there is the possibility, the book talks about this a little bit, that, well, what if we pull in 2 double bonds, and we make 2 double bonds here, and we lose these lone pairs off of those 2 O's in the process, and then in doing so, we reduce those formal charges of those O's down to 0 because they're now 6 minus 6. And now that central sulfur has a 0 formal charge. And so we've changed sulfur down to 6 minus 6 for 0, and 2 of the O's down to 6 minus 6, but we still have 2 of the O's at minus 1. So 2 O's are still minus 1 formal charged as they were before. 2 of them are now 0, and the central sulfur is 0. And now there's this idea of minimizing magnitudes of formal charge, and that's sometimes referred to in the textbook as the formal charge rule, or based on the formal charges, trying to reduce those when possible. And so is it possible to reduce magnitudes of formal charge by expanding the octet of an atom? If you recall, we thought about this for nitrogen. We said categorically for a second row atom, cannot do it. So we thought about this for nitrate and said we had to stop at 1 double bond, 2 singles, and couldn't push to the second double bond to reduce nitrogen to 0, because for second row atoms, we certainly cannot expand an octet. Now, third row atoms are kind of weird in that you can actually find examples like PF5, SF6, molecules that actually expand the octet of the central atom. Now, because those molecules form, I think have led some people like like me who teach classes like this to think that sulfur and sulfate can also expand its octet. So why not expand the octet of sulfur and sulfate by reducing its magnitudes of formal charge? Now, the only problem is that there's really no orbitals that are available to do this. In the next chapter, we'll talk about some orbital models for how we can have overlapping of the atomic orbitals to make molecular orbitals. And there's just no orbitals that are really available to make these double bonds. There's no theoretical support in terms of modeling of molecules that supports calling these bonds double. But the book leaves it a little bit open-ended, a little too open-ended in my opinion. So I think we should say that these probably don't form, and these probably aren't very likely to form. But if they did, you'd have to then somehow picture resonance would kick in. It would then, you could sketch a bunch of different Lewis structures where the double bonds move over to these O's. And then you could also go through all the different permutations of two doubles here, two singles, two doubles over here, two singles there. It becomes maybe a tedious process to write and consider all those resonance structures, but somehow through resonance, the sulfate bonds all end up equal in length. So I think that the bigger question would be, for sulfate, regardless if you think this is a better Lewis structure, or if we just resketch this one here, let me quickly resketch this Lewis structure here and say, if we're trying to determine which of these Lewis structures is best for sulfate, I think it's clearly this one here, and it's not this one here. The book leaves it a little too open-ended in my opinion, but I think we're not gonna ask you for sulfate, is it better for it to have 4 single bonds or 2 single and 2 double? The better question is just to ask the more realistic question, which is, are all the bonds equal in length in sulfate? Because it doesn't matter if you think it's, let's call this one structure A, let's call this one structure B. It doesn't matter if you think it's A or B. What matters is that you recognize if it's B, all those bonds resonate and all the bond lengths are the same regardless. And so all these bonds in sulfate are equal in length because they're all single bonds, are all identical to each other. So I think the key detail is that all the bonds in sulfate are equal in length. So that if you do think it forms structure B, that it's somehow resonating those bonds such that they're all the same as each other. We don't really, in sulfate, have 2 double or 2 singles. Those would average out somehow if we really had this structure B. If you just leave it as structure A, you don't even have to think about resonance. You just see one structure that shows you 4 equivalent SO bonds. And so hopefully what Lewis structures show us is what type of bonds do we have, what bonds are similar or different from each other. Can we start to predict single bonds longer, double bonds shorter? And so when we have a structure that shows a single versus a double, we want to know, is that real or is that just like something that's going to resonate? And let me come back to something just really straightforward. Like when you look at, remember how we did formaldehyde, we had this Lewis structure here. Like this is what we call a localized double bond. Like when I look at this Lewis structure here, like that's a real double bond. That's a double bond exactly where we think it is. And so that's like an ordinary, like what we call localized double bond. And localized just means it's right where you think it is. It's not being spread across other centers. When I think of like the acetate ion, so the acetate ion, which is CH3C, I'm not going to go through the task of actually showing you how to get to this Lewis structure. I mean, we could, but that's, but once we get to a Lewis structure, it looks something like this, where I have a minus charge here, and I have neutral atoms everywhere else in terms of my Lewis structure. This structure here is a delocalized picture, because I can move these electrons here, and then put the electrons back on this O, so I can have CH3, C, with the bonds here. And so what I hope you see is that the process of moving those electrons around and resonating them is the process we call delocalization. And so this is delocalization, or we call that extra double bond. In the acetate ion, we call it a delocalized double bond because it's being spread across 2 atoms simultaneously. And so the real structure would look more like this, where those bonds are exactly equal to each other in their properties. So these bonds would actually be equal in length in the real molecule. So the 2 CO bonds in acetate ion equal in length. We don't have one double shorter, the other one single longer, because it would just resonate across with the other bond at all times. So we have to think, if I can sketch equivalent yet different Lewis structures, the molecule is never compelled to exist as a Lewis structure we write on paper. We're just trying to understand what we can learn about a molecule through a model we call Lewis structures. Just because we can sketch a Lewis structure doesn't make nature be forced to adopt the thing we wrote on paper. So just remember, Lewis structures are models trying to help us understand what we can learn about the different types of bonds, the different types of lone pairs, and then this effective resonance in molecules. Okay, this is showing us some bond length trends. There's probably a lot we can talk about with bond lengths, like where, and bond strengths, where the strength of a bond is going to be kind of related to a couple details. Like, for example, if you think of HF, where we have probably the most polarized covalent bond that you can have, if we find HF on our chart here, that is right here. And so 567 kJs per mole for HF. If you notice, for our single bonds in this chart, that's about the highest of any of those bonds on the chart. So having a polarized bond is creating partial charges. Partial charges give you electrostatic forces of attraction that you don't get if you don't have those charges. So if you look at bonds that really don't have much of a polarity difference, like the CH bond is not as strong, 413 kJs per mole, the carbon-carbon bond, 348 kJs per mole. So lacking a big set of charges on your atoms is going to weaken the bond. And so polarizing bonds generally strengthens bonds because it creates charges, electrostatic forces of attraction. But then a big impact on bond strengths, if you compare the carbon-carbon single 348 to the carbon-carbon double 614 kJs per mole. So single to double bonds, you see a big strengthening of our bond strengths. If you go to the carbon-carbon triple bond, even stronger. So triple bonds stronger than double bonds, stronger than single bonds, and we're comparing with the same atoms. And even if you look at the magnitudes of our multiple bonds, the magnitudes of those bond energies are a lot higher than their single bond analogs above them. So if you look at, like a carbon-oxygen single, 358, carbon-oxygen double, 799. So a lot stronger in the case of our double and triple bonds. Carbon-oxygen triple bond, 1072 kJs per mole. So one consequence should be that single bonds are weaker than double bonds, weaker than triple bonds in terms of strength of the bond, or the energy it takes to break the bond. And then in terms of length, the bond length, of course, we know that single bonds are longer than double bonds, which are longer than triple bonds. So the bonding pair electrons are acting like glue. So the more bonding pair electrons are shortening bonds, and then also, in effect, strengthening bonds. One other detail, and I don't think we'll talk too much about predicting bond length trends in terms of, I don't think you'll see a question on the test that says, oh, this bond's more polar than another. Do you expect its bond strength to be higher or lower? Interesting questions and interesting relationships. If you go to like an I2 bond, really big atoms. So you might imagine two big iodine atoms with a single bond, notice how weak it is. So long bonds generally are weaker than shorter bonds too. So if you can shorten a bond, if you can strengthen the bond through polarization, generally you're going to have a stronger bond. And certainly if you strengthen that bond or shorten it through adding more bonding pair electrons, then of course you add a lot of strength to the bond. Okay, this slide here is just showing you a couple bond length trends for, single, double, triple. So for carbon-carbon, you see 1.54 angstrom, longest for single, about 0.2 angstrom shorter for double, and not quite, but about 0.2 angstrom shorter for triple. And you see the same trend for carbon-nitrogen, single, double, triple. You see a shortening of the bond as you go from single to double to triple. And this is replicated for all of our groups here where we can have comparisons between CO single, double, triple. So we're seeing in every case the single bond's longer than the double bond, which is longer than the triple. And then that's then inversely related to the bond strength. The triple bond, of course, is the strongest. So in terms of strength, strongest, then weakest, and then even weaker for the single bond. Okay, so this question here, I probably could have thrown this out because we already talked about it before, but in sulfate, no matter what Lewis structure you sketch, we talked about this earlier, that whether you're thinking the Lewis structure is this one here, these are all singles. So all single bonds. Where I think a good rule, and back before we had common exams when I would just write my own test, I would just say never expand an octet through multiple bonds. Just stop at an octet. And that's generally a good rule of thumb, especially since we're not going to really test you too much on, coming up with these combinations here where you might minimize magnitudes of formal charge. But if you come up with this Lewis structure here, maybe it's possible to write it, understand why we're writing it, but that it's probably not as good of a Lewis structure. But even if you did sketch this Lewis structure, I just want you to know that all those bonds would resonate such that all of its bonds are going to equal in bond distance. So for sulfate, a key property is all 4 of its bonds are equal in length. This is probably, again, the better Lewis structure. This is probably not the best Lewis structure, but even if you want to sketch or call that the best, just imagine resonance taking place to equalize all those bond lengths. You just have to picture all of these permutations to maybe understand how those electrons are distributing and spreading out at all times across sulfate. So you just be picturing that you have something that kind of looks like this for a sulfate with the double bonded Lewis structure. Let's talk about a couple exceptions to the octet rule. We'll see some exceptions for diatomic molecules when we're deficient of an octet. And these are things that tend to be maybe more atmospherically related, like hydroxyl, radical, NO, CLO. These are more things that are commonly found in the atmosphere. Now, if you think of like the OH here, this is like OH minus, but without the minus charge. And so if we're calculating the number of electrons, we only have 7 electrons to go around for the OH radical. So how do we sketch its Lewis structure? Well, the way I would start is, well, we have to at least single bond, and then we only have 7 total electrons to distribute. So I only have this many left over to put on O. So that gives me 5 for O, and then plus these 2 here. So that's my 7 electrons for that molecule. If I think of my formal charge on O, it's not too bad because it's 6 minus 6. Should have 6 electrons for neutral charge, and I do in the Lewis structure. So I have a 0 formal charge on O, a 0 formal charge on the hydrogen. And so if I had an extra electron, it would add on to the O. So if I had the OH minus ion, so hydroxide ion, of course, would just look like this here, where we'd have that extra electron. And so the hydroxyl radical, if we lose an electron, we're just kicking an electron off of O. There's nowhere else to kick one off from in the structure. And so this would be what the hydroxyl radical would look like. Now, NO, how do we think of the Lewis structure for NO? 5 plus 6, that's 11 total electrons. What I would probably do, probably an easy starting point, is to imagine we kind of have that negative charge. So add that extra electron. Let's think of NO minus first. So let's think first NO minus. So 12 electrons for NO minus. And so if you recall, we did this Lewis structure, I think it was last time. But we'd have one just like O2, where we have a double bond, and then we'd have 4 electrons as lone pairs on each of the N and the O's. And that's if we have NO minus. If you recall, the minus charge was on the N. So for nitrogen, we had the negative formal charge on the nitrogen atom because 5 minus 6 was minus 1, and then 6 minus 6 for 0 for O. So that's how we were getting the formal charges here previously. So that was our NO minus Lewis structure that we worked out before. So for NO, we can actually make use of that formal charge rule. So the formal charge rule would say if I have to kick an electron off, so if I have to lose an electron to make NO neutral without the negative charge, so I have to lose an electron. The question would be, do I lose this electron or do I lose that electron? Which one of those 2 electrons do I want to lose? And so let's compare the 2 alternatives. So let me start by losing this electron here. Let me change my formal charges then. And so if I lose the electron off of N, my formal charge would be 5 minus 5 for that nitrogen, now neutral, and oxygen remains neutral at 6 minus 6. And so that doesn't look too bad. And so what if I instead had taken the electron off of the O? So if I take the electron off of O, I'm going to remove one of the electrons here. And so then that for oxygen gives me just 1, 2, 3. Oh, I forgot to sketch the double bond. So for oxygen, I have 1, 2, 3, 4, 5 electrons surrounding it. So I have 6 minus, not 6, but 6 minus 5 for O, for plus 1. And then nitrogen is minus as that initially was, 5 minus 6. And so now if I'm choosing between these 2 Lewis structures, I have NO with nitrogen having lost an electron from NO minus, or if I have NO where I have oxygen having lost an electron from NO minus, which one do you think is better and why? The better structure is this one here, because we're going to apply the idea when we have equivalent Lewis structures in kind of what's being shown. So what I have in terms of equivalent Lewis structures, what I mean is I have a double bond in both, I have the exact same number of lone pair electrons in both, one atom's violating the octet rule in each, one atom satisfying the octet rule in each of the Lewis structures. So the difference is just which atom do we want to violate the octet rule in. Well, think about the magnitudes of formal charge, how they can help us. The magnitudes of formal charge in the first structure are 0 and 0. And in the second structure, they're now maximized at minus and plus. And so on one hand, it's probably bad to put a positive charge on O, but it's not even necessarily that we have the positive charge on O that's bad. The problem is that we've maximized the formal charges and we could have minimized them. So we want to minimize the magnitudes of formal charge when possible. So the application of what we sometimes refer to as the formal charge rule is if we're choosing between Lewis structures that look to be similar or as equivalent to each other as possible, we want to choose the one that minimizes the magnitudes of formal charge. And so we minimize the magnitudes of formal charge with NO, with the nitrogen being deficient of an electron. What about ClO? Well, for ClO, where we have 7 plus 6 electrons, that's 13. So I probably go to ClO minus. So let's think about plus 1 for ClO minus first, and let's think about which atom we want to kick the electron off of. So for ClO minus, we'd have, and we've done that Lewis structure, I believe we did that last time as well. But for ClO minus, we'd have this Lewis structure here with the minus formal charge on O. It looks like the same basic Lewis structure as Cl2 or F2, where they also have 14 electrons. So we have 14 electrons, we just go with the single bond. And so then the question for ClO, if I want to kick the charge off, do I want to kick the charge off of chlorine, or do I want to kick the charge off, or the electron off of oxygen? And so those two Lewis structures would look like this one here, where I leave the electrons on O, but I kick one electron off of chlorine, or I go with the structure where I leave all the electrons around chlorine and kick one off the oxygen. Okay, so let's calculate formal charges. So the formal charge here should have had 7, I only have 6 now, so that's positive for chlorine. And now oxygen is still minus as it was, 6 minus 7. So just break the bond in half. How many electrons are closest to O? There's 7. Should only be 6 for a neutral charge. That's how I get minus. And now my Lewis structure on top, chlorine's 7 minus 7 for 0. And then the oxygen has lost an electron. It's now 6 minus 6 for neutral. Okay, now this one's kind of tricky in a way because this looks so good. It looks good to have a minus on the O and a plus on the chlorine because we know oxygen's more electronegative. Fluorine's the most electronegative element, oxygen's second. Nitrogen and chlorine are the next most electronegative elements. The next most after N and Cl are sulfur and bromine. Those are the most electronegative elements. So so when we see those elements paired up with other things, we know we're going to have something that we generally think of as being polar. We have NO and F involved. We're probably going to get things that are really, really on the polar side. But it might seem like this is good to have the negative on the O, the positive on the chlorine, but we're maximizing formal charges. We want to minimize formal charges. And so the best Lewis structure is the one on top. It's the one that puts the 0 charge on chlorine, the 0 on oxygen. And then you can think, once you get to that Lewis structure, think about the bond shading probably more towards O because it's more electronegative. So oxygen's going to have a bigger pull. So it should be partial negative. Chlorine's going to be partial positive in their true charges, but the best formal charges, the best Lewis structure, would have a single bond, electron deficient on O. Then think about how oxygen's going to pull electrons more towards itself and pick up some kind of negative charge. So I think the problem with the positive negative Lewis structure is you would probably think oxygen goes even more negative than -1 if you thought of that Lewis structure as being best. So once you go to that Lewis structure, you think there's this big negative charge on O, you're going to then say, well, oxygen's still more electronegative. It should pull the bonding pair electrons closer towards itself and go beyond -1, and it really doesn't. So to really think of the best Lewis structure, when we're choosing between Lewis structures that are pretty similar to each other, choose the one that minimizes magnitudes of formal charge, all else being equal. There's other exceptions that we see. We've already seen some of these, like BF3 is a case where we found a Lewis structure like this. We can double check our count here in a second. So boron should have 3 valence electrons, or boron does have 3 valence electrons. 3 times 7 for the fluorines, that's 24 total electrons. that we need to show in our Lewis structure. So we go with this Lewis structure here with 3 single bonds. And so then we don't go with this Lewis structure here because now this is maximizing formal charges. So that's bad because it would increase magnitudes of formal charge. And so we leave ourselves with this Lewis structure like this, where we have 0 formal charges all the way around the molecule. And it just so happens that the central atom doesn't have a filled octet, and that's okay. So the octet rule, I don't think is so much a driving force for atoms as much as we maybe make it seem so, especially maybe at the lower ranks of chemistry into high school when you were learning about the octet rule. So the octet rule isn't so much a driving force as the balance of charges. So boron having a charge that it can actually sustain is probably more important for boron. So it being neutral in charge here is probably good for it, because if it builds up too much charge, it's not going to be quote unquote happy as a result. And so boron, BF3, can exist as a stable molecule without satisfying the octet on boron, because that's about how much charge its nucleus is capable of holding on to. And then the fluorines are happy because they're trying to pull electrons back off of the fluorine, or back off the boron. So the fluorines are really polarizing themselves negative and almost making what looks like a hybrid between being a perfectly covalent compound and some kind of ionic compound. If BF3 were ionic, it would be F minus, F minus, F minus, B3 plus, through a molecule somewhere in between that, where boron really has some partial positive. BeF2, something similar. Beryllium F2. Beryllium only has 2 valence electrons, 2 times 7 for the fluorines, at 16 total. So we end up with a Lewis structure, looks something like this. And so then for beryllium here, it's happy not satisfying an octet. We don't want to make 2 double bonds. We don't want to increase magnitudes of formal charge. We want to decrease magnitudes of formal charge. The formal charges are 0 all the way across. Fluorine's trying to pull electrons towards themselves because they're a lot more electronegative than beryllium. But beryllium is still electronegative enough that it doesn't go full Be2 plus like something like magnesium would do. So if we had magnesium fluoride, magnesium would just be Mg2 plus, F minus, F minus, where we'd have the fluorines having stolen the electrons off that central atom. Here, the beryllium's keeping the electrons a little bit around itself, so it stays partial positive, not quite fully 2 plus, partial negative for the fluorines. So we'll see exceptions for having an odd number of electrons, not satisfying an octet for that reason, and sometimes we'll be deficient of an octet for cases for things like boron, beryllium, etc. So we don't always have to satisfy the octet rule within a stable molecule. And we previously have seen a bunch of examples of compounds that expand their octet. Those would be things like PF5, SF6, molecules that just have a lot of central atoms. And those molecules do exist, like SF6. There's a demo. I hate doing it. I wish I didn't hate doing it because it's really fun to breathe in SF6, which makes your voice very deep, kind of the opposite effect helium has. You breathe helium in, makes it high. Breathe SF6 in, it makes your voice very deep in its sound. And it sounds pretty cool. I've done it once, but the fumes feel so weird coming out, and I really don't think it's safe to do that demo, so I don't like doing it. But if you go online, you can probably see other people doing that demo. But SF6 is a real molecule. It's that you can actually supposedly breathe in for like lecture demonstrations. Okay, let's do a couple more Lewis structures where we can hopefully see how like this formal charge rule kind of plays out. For the most part, there's like one question on the test I don't like that doesn't follow this rule so closely. I can't obviously tell you the question, but when you get to the question on the test, it will make sense. Generally speaking, if I say a formula is NCO minus, it's going to be N, then C, then O. Now, there's one molecule in the test that has a weird formula where it doesn't actually follow that linear sequence, but you'll see some structures that'll make sense when you see it. So in almost every case, if I'm writing NCO, I don't want you to consider C, then N, then O. I really want you to consider N, then C, then O. And if we wanted you to consider some other order, we'll show you the order. So we'll help you out. So some molecules, identifying the central atom is tricky, but I don't want that part to be tricky because usually the way we do this in formulas is we structurally give you the information to know the right ordering of the elements, or we show you through structures or through examples within a problem how to connect the atoms. So in other words, I don't want this part here to be the confusing part, that we go from N to C to O, because that's just the order that we wrote the atoms. If I wanted you to have nitrogen in the middle, I would have called that CNO minus. So if I wanted nitrogen to be in the middle, I would have written the formula differently. And that's almost always the case. Like I said, maybe there's one exception, but it'll be obvious when you see it. So I don't want that to be confusing later when you say, hey, that didn't follow the general trend. So just know usually we follow the trend that we give you the atoms in order, but occasionally we will give them to you in a different order, but we'll help you understand through other ways of knowing what the proper central atom is. Okay, so with that said, if I think of my usual Lewis structure rules, my Lewis structure rules would be take the nitrogen valence count, the carbon count, the oxygen count, add 1 for the negative charge. It's easy to miss the negative charge, but the -1 adds 1 electron. And so that count here would be 16 electrons. I had to add the electron. So 16 electrons. I started with this minus because I just wrote it too quickly, but the -1 charge, we add an electron. If we have a positive charge, we take the electrons away. So 16 electrons have to be shown. So I go to this Lewis structure here. And so then from there, I start thinking, okay, I have a deficient octet on carbon. What's its formal charge? Should have 4, it only has 2, it's +2. Oxygen should have 6, it has 7, -1. Nitrogen should have 5, it has 7. 1, 2, 3, 4, 5, 6, 7. For -2, not +2, but -2. Okay, so this little structure here is definitely not the best yet. So we want to make some double bonds. We're just going to have to be selective in which ones we make double bonds with. And so if we make a double bond here, that's going to be good because we take the formal charge for carbon down to 4 - 3. That's plus. And then we kick the 5 - 7 down to 5 - 6 and change the formal charge in that nitrogen to minus. And so that's good. We've gotten to a better Lewis structure, still not best because carbon's still deficient of an octet, still has a positive charge. So do we want to make a second bond with carbon and nitrogen, or do we want to make a bond with carbon and oxygen over here? So another possibility might be, well, what if we did this Lewis structure here? What if we do this Lewis structure here? This doesn't seem too bad because we have a 0 here, we have a -1 here, we now have a 0 formal charge on the central carbon. So that's not a bad idea. That's just taking, this electron pair here and making that Lewis structure. Well, what if we said, well, what if you make the Lewis structure over here instead? So what if we make this Lewis structure for N triple bond to carbon and then leave the single bond to oxygen on the other side? That doesn't look too bad, right? Because now we have a 0 formal charge on nitrogen, we have a 0 formal charge on carbon, and we have a minus formal charge on oxygen. Now you can even say, well, why don't we make the triple bond over here as another possibility and leave the nitrogen as a single. And so of these, you can even say 4 possibilities. Should we stay here? Should we go to here? Should we go to here? Should we go to there for our best Lewis structure? What do you guys think? So now when I'm looking at my formal charges, I'm going to reject this one right off the bat. So I'm going to reject the lower right off the bat because its formal charges are too high. I'm not minimizing formal charges with that structure. And I'm also not minimizing them with this structure either. I'm minimizing them equally with these two structures here, but the question then becomes, would I rather have the minus charge? So all else is equal. 0 formal charges on everything except, do we want N to be minus or do we want O to be minus? I think we want O to be minus. So this is going to be better to keep O negative here. So again, we have to think, what is it that we're comparing? If it's the CLO example previously, it was minus plus for 0, 0, 0, 0 was better. This one here, I'm not comparing zeros versus minus. I'm comparing negative on the O versus negative on the N. So the only difference is this charge here. We would rather have it on the more electronegative atom if possible. So if all else is equal, put the negative charge on the O. And in this case, we're comparing all else being equal. We can put that negative charge on the O. N2O, N being the central atom, has a very similar kind of Lewis structure. It's so similar, it's almost the exact same example, but just with slightly different atoms. It has one additional Lewis structure you might consider. So if nitrogen's the central atom, we're told that here. So we have the same starting point as the CNO minus example above. And so then again, the question kind of becomes, do we want to do a double here? That's a good idea. Do we want to do another double here? That's a good idea. The formal charge on nitrogen at this point is 5 minus 4 for plus, and oxygen's minus, nitrogen's 0. And so that looks to be pretty good. And so if we're then choosing between, is that the best Lewis structure, or would this be better? And that's not better because it's putting the negative on the end. It's kind of the same example as above, where we probably don't want to put the negative charge on nitrogen. So this doesn't look like a better alternative to this Lewis structure here. But there's one structure I want to make sure that we see is categorically wrong, which is this one. What about this structure here? Why is this so bad? So if we make a double and a triple, so what's so wrong with this structure here? This is just making an extra double bond to reduce that formal charge of nitrogen down to 0. Why do I not want to do this Lewis structure? Doesn't that look good? Because everything's 0 here. We're just talking about minimizing magnitudes of formal charge. Should we minimize magnitudes of formal charge? No, because we're expanding the octet. We can't expand that octet of nitrogen past 8 electrons. So categorically can't do that last structure there for N2O. Okay, so we'll start class with this example next time to kind of wrap something up from chapter 8. And then we'll get into some chapter 9 concepts. I got a couple quick demos to do. One is kind of, so let's start with the pickle demo. So what I'm going to do is I'm going to electrocute this pickle. This ordinary pickle. Turn lights down. So what's going on is the sodium and the nitrates from the pickle are forming sodium metal. You're kind of seeing a flame test of sodium. So that's kind of what sodium looks yellow when it burns. So we're taking sodium plus through the absorption of energy, taking it back to sodium neutral. So through energy, we can power that reaction to form sodium metal and then see a quick flame test. And now one other demo. Let's get some lights back on. Is who here has seen elephant toothpaste? Who's seen that demo? Have you ever seen it in a pumpkin? Have you ever seen elephant toothpaste? If you haven't, you'll know what it means here in a minute. Have you ever seen elephant toothpaste? Usually do it in a flask and it shoots up in the snouts. Here we are making basically through soap and a reaction. We're just bubbling up soap. So we're forming pumpkin toothpaste. All right, so those are our Halloween demos for class today. We used to blow a pumpkin up. We're going to try to do that if we can later. We have some weird clearance issues with doing fire demos in lecture. So we're slowly being able to reduce some of them. Hopefully we get to blow something up that's full at least a few times before the end of class. So that's it for today. I will see you guys back here on Friday.